Welcome. I'm Xuhui Hu. I'm from Southeast University in Nanjing, China. In this work, we present a real-time myoelectric decoding model for continuous hand motion recognition using an automated data labeling method. Gesture recognition is one of the most significant research contents in human-robot interaction. State-of-the-art technology, including data glove, exoskeleton device, and computer vision, have achieved excellent performance. Recently, hand recognition based on surface electromyography has become a new hotspot, which has the advantages of comfortable wearing, unrestricted handshake, and outdoor usage. The contribution of this paper is represented as follows. Firstly, we streamline the dataset collection procedure for real-time myoelectric decoding model. Secondly, this model has the capability of predicting multi-degrees of freedom simultaneously and continuously. These gestures are only decoded from an array SEMG sensor of 8 channels. Finally, the source code is open access on GitHub. Please check the link in this slide. The core of intention recognition is to establish the mapping between array SEMG to motion level. Our idea is to first collect sufficient information, then compress the data layer by layer, and finally feed the compressed feature to the motion label. Specifically, the raw array SEMG signals were firstly undergoing pre-processing. Root mean square was adopted to filter the stochastic components. Then, we collect the temporal sequence in each array SEMG channel as an independent sample. Therefore, each sample contains both temporal and spatial information. Next, we refer to the idea of dimension reduction in muscle CG theory, which assumes that SEMG is generated by a few muscle CG features and the number of features is consistent with the number of gestures to be recognized. Due to the relatively large ratio of data compression, we first apply a lightweight linear compression algorithm to the SEMG sequences of each channel, such as principal component analysis, to reduce the difficulty of the dimension reduction algorithm. We calculate the value of R² from the time sequences before and after compression to determine the number of retained components. Then, we input the compressed features into an autoencoder, where the activation function of the encoding layer uses the ReLU function to ensure the compressed features are non-negative. And in decoding layer, the activation function uses the arctangent function to recover the negative values introduced by PCA. Finally, the encoding layer acts as the second layer of the compression network. At this time, our hypothesis hopes that each neuron compressed by the autoencoder represents one gesture, but the self-learning algorithm based on gradient descent cannot exactly learn the label information that is intuitive to people. In order to retain the advantage of unsupervised learning, we introduce an automated data labeling mechanism, which can generate intention label based on the features of the previous layer, and then use a fully connected regression neural network to learn the mapping between the muscle CG features and intention label. Therefore, we close the loop of SEMG decoding framework. The proposed hierarchical network facilitates fast training and reduces the data hungry for deep networks. To explain the mechanism of the automated data labeling, let's focus on the fully connected regression neural network layer used for mapping the muscle CG features. As a motivating example, we will automatically label a training set. Firstly, we use the sum of 6 muscle CG features to highlight the activation of each gesture. So, we get a blue oscillating waveform, in which the peak indicates the largest activation of muscle CG at a certain gesture, and valley indicates the resting state of muscle. Therefore, a complete valley-peak-valley segment represents a motion procedure from the beginning of the hand gesture to the strongest muscle activation and restore to the rest again. By searching for peaks and valleys, the algorithm can automatically reconstruct a continuous motion intention label. It's obvious that the extent of muscle activation for some of gesture is different. Therefore, it's necessary to perform a uniform normalization on different gestures. After normalization, the maximum activation of each gesture is set to 1, and the rest status is set to 0. Finally, in this learning framework, we got the value of R squared for 3 degrees of freedom in a test set, was 0.86 for rest flexion and extension, 0.89 for rest pronation and supination, 0.87 for hand open and close. Meanwhile, we compared 3 data labeling methods, that is, real motion labels from lip motion, annotation to lip, automated data labeling from array SEMG activation signal, annotation to RMS, and from muscle synergy features, annotation to MSF. As a result, MSF has better response than RMS, even better than lip during the end of the gesture. More importantly, when the kinematic signal has reached a plateau, the predicted value is still rising. The reason is that the force of gestures continues to rise even though gestures are complete. It can be interpreted that the proposed method not only predicting the gesture, but also extracting the forced variation when making a static gesture. We established a two-dimensional phase law test to quantify the real-time simultaneous performance of algorithm. In this experiment, subjects were required to move the blue circle to the red circle. Two alternative control strategies were compared. In the first control strategy, the rest flexion and extension controlled the horizontal movement of the cursor. The rest rotation controlled the vertical movement of the cursor, represented as rot. Another strategy used the same horizontal control, but utilized radial and ulnar deviation to control the vertical movement, represented as diff. Here, we found a stronger linear relationship between complete time and index of difficulty in diff than in rot. Furthermore, diff had less sharp turns in the trackpath than rot. Both results indicate diff has better performance on simultaneous control. More importantly, both strategies prove that even if the training set does not include a gesture that combines from two different DOFs, the algorithm can still achieve correct predictions when actual simultaneous gestures occurred. With this myoelectric decoding model, we use the predictive value to control a human hand in a unit 3D environment as an interactive medium for virtual reality. In this application, the continuous and simultaneous gestures are intuitively illustrated in a virtual hand, as well as the force variation during a static gesture. In another teleoperation application, we use the same recognition result to control a robot hand. A proportional myographic control according to the velocity of movement is utilized to complete a grasping task. At last, we apply this model to upper limb amputee recognition. Further work needs to be polished on implementing more long-term experiments, as well as the reliability experiments for disabled with different degrees of amputation. Thank you.